Can everyone hear me? Okay, perfect. Okay, hello and good afternoon, everyone, and welcome to this edition of the Hong Kong Institute for Advanced Study Distinguished Lecture Series. It is my pleasure to introduce and welcome the speaker for today, Professor Etienne Ghys. So before we begin with the presentation, I'm just going to provide a very brief biography of the speaker. So Professor Etienne Ghys is a well-renowned French mathematician who has done a lot of significant contributions in various different research areas, which include topology, geometry, and also dynamical systems as well. Beginning his PhD a number of years ago, working on affine groups, he's looked at a number of different areas and trying to look at the intersection and connection of these different topics. As he is a well-renowned mathematician, he has received numerous awards and also been invited to various different prestigious conferences. This includes being invited to the International Conference of Mathematicians in 1990 in Kyoto, as well as being invited as a plenary speaker in 2006, where it took place in Madrid. As well as this, as I've mentioned, he has won numerous awards, which include the 1991 CNRS Silver Award, as well as the 2015 Clay Award for the Dissemination of Mathematical Knowledge, and then more recently, the 2022 award given for the Mediation Medal given by the CNRS. As well as being a famous mathematician, he's also been very prominent in the spread of mathematics in terms of the general audience. This has included books, audiobooks, lectures, and some of this has also been used in classrooms within schools. So today, Professor Ghys is going to be speaking about a very interesting topic, for me at least anyway, at the intersection of sports and mathematics, which is entitled Soccer Balls, Their History, Geometries, and Aerodynamics. Finally, I would like to say the City University of Hong Kong thanks you for accepting this invitation and welcomes you again. The floor is yours.
Thank you very much for the invitation and the nice words. Indeed, I want to discuss a topic which is not classically studied in mathematics, soccer balls. You have here 3 balls. Each ball has a nickname. This one is called Telstar, this one is called Brazuca, and the third one is called Alrila. So what I want to do today is to show you that these balls and all the balls that are used in soccer are beautiful and full of mathematics and full of physics. So let me begin by telling you that there are many, many different balls. So this is the list of all balls which have been used by World Cup since the beginning. And the World Cup is not the only competition. So there are many, many different shapes of many different balls. And most people never looked at balls. So I want to show you that if you look carefully, you'll find beautiful geometry, beautiful physics, etc. So let's begin by the Telstar. This is the most famous ball that we all know, with black pieces and white pieces. I'm pretty sure that if you ask anybody, like you for example, how many black pieces are there? How many, do you know? So let's have a better look. So this famous Telstar is made of pieces. Some of them are black and have 5 sides, pentagons, and some of them are white and have 6 sides, hexagons. So how can you count the number of black pieces? Well, you can see here on this picture, you can see 1 in the middle and 5 around. So you can see 6 of them. You can guess that the opposite side of the ball has the same number. So you have 12 pentagons. And if you count carefully, you will find 20 hexagons. So I want to tell you that these 12 and this 20 is not random number. They come from history of mathematics. And I will tell you a few about that. First, why this name Telstar? Well, it was it's written here, the official World Cup ball in Mexico, 1970. And 1970 was the first year where you can see competition of football competitions on television. Before that, you could not see that. And at the time, of course, the television was black and white. So it was important and the screens were very small. So it was important to produce balls that you can see easily on a black and white small screen. And this is called Telstar because this is a star of television. Now, let's have a better look at these balls. A few months ago, I had the idea of joining a group of kids, about 10 years old, and I put a ball in the middle of the room. I gave them paper and pencil, and I asked them, can you draw what you see? Not just by memory, they had the ball in front of them. And this is what I got. You see that this picture is not easy to understand, and some of the kids are kind of strange, like this one is more an artist than the mathematician. And I just want to explain first that this shape is far from obvious. It's very difficult to draw it, to understand it. Let me show you another proof that the shape is not obvious. This is a sign that you see in England showing the stadium, football stadium. If you look carefully, you'll see that the black pieces are hexagons, not pentagons. This is a mistake, big mistake. And there was a complaint. They wanted, some mathematicians sent a complaint to the government, asking them for a change in the shape of these signs, and they didn't want to do it. And the argument was that the government has nothing to do with geometry, which is kind of So this is a mistake. Here's another mistake. This is the official logo for the Champions League. And if you look carefully, this picture is completely wrong. You see here, this white place is surrounded by 4 stars. And the other one, this one, is surrounded by 3 stars. This is completely wrong, and I cannot even imagine how the web designer charged for this picture. So this is wrong. Here's another example of a ball. It looks like a ball, but it's not a ball. As black pieces are hexagons, it should be pentagons. So this is my first comment. When you do geometry, you should look carefully. And most people never looked at the soccer balls. OK, so that's the same picture, except that it's centered on the white piece. And let me ask you, how many symmetries are there in this ball? You see that if you take this ball, and if you rotate it by 1/3 of a turn, the ball takes the same position. So the center of each white piece is the center of rotation by 1/3. If you look at the black pieces with pentagons, you have a symmetry of order 5. If you take the middle of this edge, you can take a rotation of order 2. So if you count how many symmetries in total you have, some symmetries of order 5, some symmetries of order 3, some of order 2, and in total you get 120 symmetries. And it is a famous theorem that among all polyhedron, the highest possible symmetry is 120. And this is obviously the reason for this. You could believe that this shape is due to Adidas, but no, you have a beautiful picture drawn 500 years ago by Leonardo da Vinci in a beautiful book called De Divina Proportione. And this is a wonderful book with many different shapes. He was interested in understanding nature, understanding the structure of physics, I would say, what is at the basis of physics in space. And you have to come back to Plato. Long time ago, he proved a wonderful theorem that if you want to produce polyhedron whose faces are regular polygons, there are only 5 possibilities, not more. The tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron with 4 faces, 6 faces, 8 faces, 12 faces, and 20 faces. There are no other choice. And the question is, what's the relationship with soccer? Plato probably did not play soccer, but what he did is that he tried to understand the nature of space and time using these symbols, the elements, the famous elements. On the left, it was associated to fire. On the right, was associated to water. And here's a picture to show you how to construct very simply dodecahedron, icosahedron. Very simple. You take 3 business cards, and you put them in this position, and you get an icosahedron. Now, start with an icosahedron like that. It does not look like a soccer ball, because it's not round enough. If you want to make it rounder, the idea is very simple. You slightly chop the vertices. And in this way, you introduce at each vertex a small polygon. And then you chop a little bit more. Then you see that you have hexagons in green. And these hexagons are not regular yet. But if you chop a little bit more, at some moment, you get the telstar ball. So the telstar ball is nothing more than a truncated icosahedron. It's made of pentagons, regular pentagons, and regular hexagons. Actually, if you want to be very careful, if you say, okay, let me chop these vertices a little bit, and you want to make, you don't want to make it regular, but the roundest possible shape, it turns out that the best solution is not really to use a regular hexagon. And if you measure in detail a soccer ball, you will see that the hexagons are not regular hexagons. They're almost regular, but they're not regular hexagons. Okay, now, of course, if you want to produce a ball, like on the right, you have to inflate the polyhedron that you built. But I will show you later that this inflation is not necessary. And with the other ball that you will see, you don't need air. It's automatically the shape of the ball. OK, so this has 120 symmetries. It's the champion in terms of symmetry. Nothing has more symmetries than this telstar. Now, why did I mention Archimedes? Because Archimedes, long time ago, tried to go beyond Plato. Plato had found the 5 possibilities for polyhedron made out of regular polygons. But what Archimedes did was the following. He tried to find all possibilities for polyhedron with faces, with regular faces, but not necessarily of one shape. For example, for the soccer ball, you have seen that you have pentagons and hexagons. Can you find more? And Archimedes showed that there are 13 more possibilities. And you have here the possibilities. The telstar is here. There are 13 possibilities of creating polyhedron made out of polygons of different shapes. And you will see later that Adidas, all the soccer balls of today, are just ideas from Archimedes. So all balls come from one of these 13 shapes. This is a picture of a molecule, which is artificial molecule, does not exist in nature, has been created in 1985. Some people call it footballen. It's exactly the shape of the telstar. It's very useful for drugs. Okay, let me go to my second ball. This ball is my favorite. It's a Brazilian ball. It was the ball for the cup in Brazil. You can see the greatest player of all times, Pelé. And when you see this picture, first of all, I think it's beautiful. And second of all, when I saw that for the first time, I was surprised, because it does not look like a dodecahedron or like a icosahedron. It looks like a different shape. And immediately when I saw that, I said to myself, it is a cube. So I'll try to convince you that this indeed I'm right, and this is a cube. Believe me or not. Okay, okay. This is a picture of this bazooka. You can see here a vertex with 3 pieces coming on this vertex. Just like if you take a cube, take a vertex, you have 3 faces are coming there. So I claim that this is the same shape. Let's have a look. You see that on these balls you have these beautiful shapes which look vaguely like a cross. And this cross, I call it a square. So let me explain that. You have 4 yellow points. When you connect them by these dashed blue lines, you create a square. You have a square, a blue square. Now if instead of connecting them by a straight line, if you connect them by a curved line, like the red dashed line, and you do that for the 4 sides of the square, you get this shape which is made of 4 vertices and 4 curves, which are identical, and the object that you get is this beautiful cross, which is a curved square. The only difference is that the sides are not straight lines. If you try to build a cube like you used to do when you are a kid, take 6 pieces, you have 6 squares, and you glue them exactly as you would do if you would like to create a cube. Here's a picture. Oops. You glue these 6 squares exactly in the same combinatorial way as you would do for a classical cube. And when you do that, these faces in a natural way, they are somehow curved. And the total result is the ball, is the bazooka. And you get the bazooka. So indeed, the bazooka ball is a cube, except that the faces are not usual squares, they are curved squares. Actually, if you want to, no need to inflate them. They're naturally curved. Now, this is, okay. Now I want to say that behind that, I have no idea if the engineers who created this ball knew it. Everything is based on the theorem of Pogorelov, 1970, which is far from obvious. The theorem is this. You start with two convex domains in the plane, a red one and a yellow one, and you assume that they have the same length of the perimeter. You cut them in paper. You have two pieces of paper, and you glue them with adhesive tape along the boundary. And the theorem says that it works fine, and at the end, you have produced a convex body in free space. I tell you, this is not obvious at all. If you glue two convex bodies along the convex domains along their boundaries with the same total length, the result is a convex body in free space. And actually, it is more general than that. You can take two domains which are not convex, and you glue them along their boundary. You want to know if you produce in that way an object in free space. And the theorem is that you can do that as long as the sum of the curvatures at corresponding points is always positive. So you can glue a negative curvature with a positive curvature point, but the total sum has to be positive at every point. And if you do that, you create a convex set in free space. And actually, this is a theorem which is even more difficult. And I think there's no simple proof today. And I have no idea if engineers who created the bazooka knew about that. Now, this is another ball. This is a Russian ball. This is the ball from the Cup in Moscow. This is just a copy of the Brazilian one, except that instead of using this beautiful curve, they used a polygonal curve. And I believe this is not as beautiful. You see, this is exactly the same picture as the Brazilian one, except that you use polygon one. The Russians have copied the Brazilians. Now let's see in practice how they do, where if you want to build a Brazilian ball, you have to cut these pieces like that, and then you have to glue them, as I told you, exactly as you would do for producing a cube, and you have this. Oops. Now I wanted to mention something else. Exactly at the same moment these engineers were creating this ball, the great mathematician Thurston had an idea, not for ball, not for football, for creating cloth. He was a pure mathematician. He said to himself, well, I want to use mathematics to improve fashion. And he tried to build surfaces. Here's his last paper. Not published, actually, because he passed away after this paper. And here's an example of what he shows. No proof, just pictures. If you cut things like that in paper, and you think of them not as being squares, but as in triangles with three vertices, 1, 2, 3. You cut 8 of them, and you glue them just as if you wanted to create an octagon, an octahedron. And when you do that, you get this ball. No proof. It's a fact. And actually, it's a pleasure to do it. Huh? It's not easy to do it, but I did it, but it works. And so Thurston began to think about how to create new shapes using flat pieces of paper and gluing them along the boundary. And let me show you example in his paper. Here's another example. So he tried to glue curved polygons to see what you could do in this way. And I told you he did that in practice. You see him trying to create new dress and new cloth. And finally, a few years later, he went to a fashion show in Paris. Thurston is here. And I think it's rather surprising that such a pure mathematician had an idea which was very, very similar to the idea of football makers. Do they know each other? I'm not sure. Now let me go to the third ball. This is the ball called al-Hila. In Arabic, it means something like travel. And this is the ball for the last cup in Qatar. When I saw this ball, I said to myself, Adidas had a new idea. At last, they did not use anymore the Archimedes principle, because it does not look like one of the 13 shapes I showed you. But I was wrong. Here's a picture. It's rather beautiful. But if you look carefully, it was not obvious to me, but I quickly understood that indeed the idea comes from Archimedes. This object is called icosydodecahedron. You see, it's made of pentagons and triangles. It's one of the 13. If I could go back to my slide, you would see this in the list of these 13 shapes. And the idea of Adidas was simple-minded. They decided to glue one yellow and one red as a single copy. So if you glue them together, you get this. You see? The red and the yellow together give some shape which is a quadrilateral, which is not regular. And so the idea of Adidas is exactly this one. Somehow it's not a new idea. Again, it's again Archimedes. Mathematicians have always the same ideas during the years. And now I want to discuss a bit of physics. Not too much, but a little bit of physics. Here's the first mathematician, which is well known among mathematicians because Tartaglia is famous for solving the equation of degree 3. But he is also well known for writing the first book on how to send cannonballs in the air. And he explained that the trajectory of a cannonball in space is this one. First, the ball goes along a straight line. After some time, the ball realizes that there is gravity and follows a circle until the circle becomes vertical, and then it falls down vertically. So his idea was that trajectories look like that. Well, it's a long time ago, no modern physics at the time. And it took a long time before we could understand better the aerodynamics and the behavior of a ball in the atmosphere. So I want to show you this, to tell you about this theorem of D'Alembert. D'Alembert in 1752, if I'm not wrong, wrote a wonderful paper. He wanted to understand what's happening to a ball, or in a more general way, body in the wind. He wanted to understand the total force that the air would impose to the body. He made the computation, very beautiful paper, and the result is 0. He proved that if you take the total force acting on a ball flying in the air is 0. So he could not understand that. And of course, he didn't know that he was using ideas. He was assuming, not consciously, that the air was incompressible. Why not? And potential flow, which is a strong hypothesis. What's amazing is that this paper of D'Alembert, at the end of the paper, there is a comment that the fact that the total force is 0 implies that the birds cannot fly. And D'Alembert says, okay, there must be something wrong in my paper. And he says, I think it's very important. He realizes, he knew that there was a difference between mathematics and physics. His paper is wonderful, perfect, no mistake, but the model that he was using for the motion of the air was not correct. So he knew there was something wrong in the physics, even though he was convinced that the mathematics of his paper was totally good. And it took a long time, and the last sentence of his paper is that it will require 1 more century before one can understand why birds can fly. And indeed, we had to wait for Navier, Stokes, etc., to understand that the key property of the fluid that helps birds to fly is viscosity. You know this famous experiment which began in 1920 or something. You have this apparatus, this object. On top, you put some pitch. The pitch is very viscous, and you wait. But you wait a long time. Every 10 years, a drop will fall. So this is fantastic. They put a camera in front of it, and you can check, I think, 10 years, 9 years, 8 years, depending on viscosity. You can see, poof, a drop falling down. This is, of course, due to the fact that this liquid is very viscous, and this is viscosity explains the motion and the force on a soccer ball or on the birds. Actually, this is a very simple picture. You have a tube, and in this tube you send some liquid or some fluid, and if the fluid is viscous, then the fluid stays sticked to the boundary. So if there was no viscosity, the velocity inside will be constant. But since there is viscosity, the velocity here is 0, is maximal in the middle. You have this shape, and this is what's happening when a bird is flying on an airplane. There is the air is glued to the surface, and this gradient of velocity is at the origin of the force. So the birds fly only because the air is viscous. Let me go to my next hero, Gustave Eiffel, the Eiffel Tower. He was a great engineer, and he constructed his tower in Paris. And the deal was that after the construction, the tower would be destroyed. But he was so proud of his tower that he wanted to keep it. So he said to himself, how can I use my tower for something that could convince the politicians that it is useful to keep the tower? And his idea was very simple. He went to the second floor of the Eiffel Tower. He took balls, objects in general, and would let them drop to the ground. and then take pictures to see the behavior of a ball falling from the second floor to the ground, to see what's happening, how is the velocity, acceleration. And he began studying that. This had a very important importance at the time because it was the beginning of airplanes. So it was important to understand how an airplane behaves in the air. So he did that during a few years, and then he had a clever idea that instead of taking a ball, dropping them from the second floor, he said to himself, maybe the best is to take a ball to send wind, much easier. And he created this apparatus close to Paris. This is very simple. You have a ball in the middle, and in the back you have a fan sending wind. You can change the velocity of the wind, and the wind is pushing the ball, and the wires there take an inclination, and then you can measure the angle, and then you can in this way easily compute, measure the force as a function of the velocity of the wind. So he did that with many balls, with many velocities, and then he discovered a phenomenon that he could not believe at first. He discovered the following fact, which is called the drag crisis. You see that. Here's the picture. Here, on the horizontal axis, you have the velocity of the wind, and then on the vertical axis, the force. It is clear that this is a picture from Ghys. It is clear that when the velocity is increasing, the resistance, the drag, is also increasing. At the beginning, it's increasing like a square. In general, we say that the force is proportional to the square of the velocity. But something strange happens at a very critical velocity, here 12 meters per second. Suddenly, the drag decreases significantly, and then increases again. This velocity is about the velocity of a soccer ball when you hit it in the penalty, for example. So he could not believe it, he could not understand it, and he tried to check it on different possible shapes, and he realized that it was strongly dependent on the quality of the surface. It could be rough, it could be smooth, it could be regular, irregular, and he made many, many experiments to understand that. Today, we understand it a bit more, but not quite. This is a phenomenon due to turbulence, which is a fact that behind the ball, you have all these strange behavior of the air. And still today, turbulence is still a big mystery in physics and in mathematics. So here's the picture of Eiffel, not for one ball, but for all soccer balls. And you see that depending on the soccer ball you use, the crisis is at different velocity. And this is very important for sports, because when you kick a ball, it starts at a certain velocity, high velocity. The velocity is high, meaning that you are on the right of the picture, and little by little the ball slows down, and at some moment you arrive at this crisis. But you see, the crisis could be here or could be here. And when you arrive at this crisis, the force changes in a very sudden way. And if you look carefully at the trajectory of the ball, you will see that the ball is initially a very smooth curve, and all of a sudden change direction. And you have to know at which velocity this crisis happens, and all goalkeepers know that. Maybe they don't know the physics, but they know that the trajectory of the ball begins as a smooth curve and then has a singularity, so to speak, and change direction. This is very important for them. And you see that this velocity, this crisis velocity, is strongly dependent on the shape of the ball. Typically, if the ball is very smooth, it's a catastrophe for sport. It seems today that the best ball is still the Telstar, which has the best crisis. You see that this is two pictures showing what's happening behind the ball at different velocities. And you see that this crisis happens exactly at this moment, where the behavior behind the ball changes in an abrupt way. This is not a soccer ball. It's a golf ball. And you see that you have a lot of small things on the boundary of this ball. This is precisely to change the crisis, drag crisis, to make sure that the golf ball does not behave in a completely incoherent way. And these things are precisely there to make sure that the trajectory of the ball is indeed smooth trajectory. Now this is the worst ball. The drag crisis is at the worst possible moment. This is Jabulani, maybe you remember this ball. It was in South Africa Cup. Nobody liked this ball. It was the players complained, the journalists complained, everybody complained because the ball was crazy. It was crazy because it has the wrong crisis, drag crisis. Now I want to mention something else. This is the picture from the famous experiment of Venturi. You have a kind of a tube, and you send inside the tube air, for example, and you measure the pressure at each point. And you see that, of course, when the tube is narrow, the air has to go quickly because the domain is smaller. And when the tube is wider, the velocity is lower. But what's amazing is that when the velocity is big, is high, the pressure is low. When the velocity is low, the pressure is higher. So this is called this is the way modern planes measure the velocity. They measure actually the pressure, and from the pressure, they can compute the velocity. And the point is that if you send a ball in the air, and if you give a spin at the ball, you see the ball is traveling in the air with a rotation, so that if you look here and here, you see that the velocity of the air relative to the ball is not the same here and here. So the pressures will be different, and this gives force going upwards in this picture. So if you give a spin to the ball, of course the ball will have a tendency to change trajectory and will not go anymore in a straight, smooth trajectory. And the consequence is that you can, in this way, organize the ball in such a way the trajectory is going in a curved way. And the most famous goal, the historical goal, football amateurs say this is the best goal ever. So it was in Lyon. Roberto Carlos sent the ball with a spin. You had four players here trying to prevent the goal. And what happened is that you can see the trajectory, which is really amazing. And you can say the player was lucky. No. After the game, a journalist interviewed Roberto Carlos, and Roberto Carlos explained how he did. And he was completely conscious of what he was doing. So, for example, I think it's amazing, he told the journalist that behind there was a publicity, advertising for the La Poste. And he aimed at the O of La Poste. So this guy was completely aware of what he was doing. And this, if you can look at this, of this game on YouTube, the goalkeeper did not believe it. Okay, so I'm almost finished. I want to show you my proposal for the next ball, for the next World Cup. I'm kind of proud of that. Let me explain how it is done. It is like a telstar. It's made of pentagons and hexagons. You see this star has 5 arms, and this star has 6 arms. They are organized exactly like in the telstar. The only difference is that the arcs connecting the vertices of the telstar are replaced by these curves. And you glue them exactly as if you wanted to create a telstar. The final result is that in a natural way, the shape is curved, and you get this, I think, beautiful shape. So I sent it to Adidas. I have no answer yet. Thank you very much.
So thank you, Professor Ghys, for that very interesting presentation and potentially that useful information that we might see this ball at 2026. So now we're going to begin the Q&A session, which is open to the audience. So if anyone has any questions, please feel free to raise your hands, and I think someone will bring a microphone to you.
Thank you. It's on? Yeah. So thank you very much for a very enjoyable lecture. All that you said, especially at the beginning, it's really tied to the fact that there are symmetries.
Mm-hmm.
So, for instance, then you end up with balls, but it would not work if you would try to get, say, an ellipsoid or some different things, in which case the symmetries are different. Would that be correct, or is it something that you could deform somehow?
You can, yes, you can deform, but you get something which is not a sphere.
No,
Yes.
I know.
You want to play rugby.
For instance, yes. So everything goes through, but then you lose some symmetries in the geometry, because all these polygons, etc.,
Mm-hmm.
they would not be the same in that case.
That's true. That's true. Yes, you're right. Just maybe one comment about these shapes. That this, I told you, the telstar has 120 symmetries, but this one has only 60 symmetries. We lost the orientation reversing symmetry. So in physics, when you would say that this object is not chiral, it is not identical to its mirror image. So this, I have to admit that this ball is not as beautiful as the telstar, because one symmetry is lost. Of course, we can glue things which are not symmetric, and you get another object which is not symmetric. But why would you do that? I don't know.
Any more questions? Okay.
Thank you very much for your talk. I will watch football from now on a little bit more attentively. So I would like to ask about the Pogorelov result. If the convex sets have corners, would still hold the result?
So the general question is a fundamental question. If you take a convex, let's say a smooth convex body in 3 space, it has positive curvature. So it gives a function on the sphere, which is the curvature at each point. And this is the reverse question. If I give you a function on the sphere, positive function on the sphere, does there exist a convex body whose curvature is this function? The answer is yes. It's a long, difficult theorem. And in order to prove that, you have first of all to prove it for polyhedron. So the answer to your question is yes, except that you have to understand the word curvature in a more subtle way. You have to understand the word curvature not as you studied in high school, but as you have to, for example, the curvature means the total angle around a single point is more than 360 degrees. But the theorem is there. This is, again, I repeat, I know no simple proof of that.
Thank you very much.
And it's unique.
I have another question.
Yeah.
Because I'm very intrigued by this last. So all these shapes, they're all identical?
Yeah, no, there are 2 shapes. One
shapes.
has 5 arms and one has 6.
Yes,
Yeah?
yes.
You have the black ones with this black one has 5 arms, and the green one has 6 arms.
So you have 2 shapes.
2 shapes.
Because if you want to cover a sphere with 2 identical shapes, is it how many possibilities? Is it one among many, or?
Well, you could. Yeah, this is. I played this game with the Telstar, but I could also play the game with Brazuca or with all the 13 examples of Archimedes. So you could imagine 13 examples, and of course, if this curve is a simple curve, but I could take another curve. It could be like a polygon or more complicated, and it gives rise to more shapes. I don't know which one is the more beautiful.
Any more questions?
Yes. Thanks for the beautiful presentation. It's quite inspiring. In terms of deformation, or how you come to this point how to prove this sort of 2 identical shapes will eventually form this sphere without a gap.
First of all, it is not a sphere. It looks like a sphere.
At least you have a symmetric.
Yeah, you know, these green and black shapes, after all, come from a shape in the plane. So when the shape was in the plane, the Gaussian curvature was 0. When you deform it by the theorem of Gauss the curvature is still 0. So these pieces, they have intrinsic 0 curvature. So these pieces are not pieces of sphere. They are close to being a sphere, but they are not a sphere. Okay? So this object is definitely not a sphere. It's not far away from a sphere, but it's not a sphere. Gaussian curvature of pieces, the curvature is located here and along these curves. And the sum of all curvature by Gauss-Bonnet theorem, the sum of all curvatures around all the sphere is 4 pi. So the curvature is well distributed, but inside these green shapes and black shapes, curvature is 0. These surfaces are called developable surfaces.
Oh, I see. Okay, thanks.
I would like to know if, so for instance, Brazuca and the Russian ball, have similar, but probably one is better than the other. Is there a precise definition of what it means to be a better ball? And if so, does it make sense to search for the optimal shape?
Well, if you ask what is the better ball, first of all, I'm not the expert for that. And second of all, to be the better ball depends on which player you ask the question. If you're a goalkeeper, or if you, which position you have in the game. And you don't have the same purpose. What? So your question would be, which one is the roundest? That's a very good question that I don't know the solution. So if you take this object, for example, I told you it's not a sphere. So there's inscribed sphere, and it is contained in between two spheres. And you would like to have an object which is as round as possible, taking the ratio of the outer and inner sphere. And you want to optimize this ratio. Answer, I don't know. I don't know. And Thurston did not know either. This is a question from Thurston.
A very simple question. You have the theorem in 1970, and you have the second theorem. Can you go back to that slide?
Oh, which one?
The theorem by Alessandro Pogorio. Theorem. I think it's Pogorio.
Pogorelov.
So this is okay. Second theorem. It says at identified points. Can you explain what is identified points? I need some identified points.
Yes, you have these two shapes, the yellow one and the red one. You assume that the length of the boundary is the same for the two. And you take these two, you cut them in paper, and you begin gluing them by the boundary. So each point on the boundary of the red piece has a companion on the yellow piece. This is what I call the corresponding ones. You have curvature at each one of these points. One is positive, one is negative, but what you want is that the total curvature is positive everywhere.
Okay, so your identified points is every points.
Yes.
Every points.
Yes.
Thank you for the clarification.
It's very interesting talk. I'd like to ask, do you find any advantage of the football you proposed for 2026?
Well, that's a good question. Let me tell you, if you look at the series of balls since the beginning of the Cup, World Cup, you see that they change every 4 years. And what is the motivation for changing the shape? Well, it's marketing. Marketing. And so my ball, I propose it as beautiful ball. But this is the only motivation.
Indeed.
Because I told you the original one, the Telstar, seems to be the favorite among players. But even though everybody knows that Telstar is the best known today, nobody wants to keep the Telstar because everybody wants to do something new. So I don't know if I answered your question, but it's a mix of publicity, a mix of everything. Money questions?
Thank you.
Any more questions?
Would you have something to say about tennis balls?
Well, I should say that I wrote a little book about that. So my next book will be tennis ball, maybe. You know, tennis ball is interesting. It's smaller. So of course it's smaller, but the consequence is that the drag crisis is much later. So the role of the drag crisis is not as fundamental as it is for soccer. And the other thing I wanted to say is that the tennis ball is not as smooth as the soccer ball, and this has influence on the trajectory too. Ah. Yeah, it's made of two symmetric parts, but they are not flat as it is in my examples. They are made of plastic or something, and they are very different. There are many balls in life.
Thank you for your talk. I've always wanted to. I'm here.
Okay.
Yeah. So I've always wanted to know why the Jabulani behaves in the way it behaves. Thank you for explaining that. I have a question about your proposed ball. So you are proposing this ball because you feel that it's beautiful. But is there a way to maybe do a test or something to know how it behaves in air, or are we going to see something that does like the Jabulani?
So you should ask somebody else. You should ask somebody else. You know, I'm a pure theoretician. I mean, I never made any experiment. When I was a student, I was very bad in physics because I could not use my hands. So I don't know. If you want to try it, try it. Yeah. Well, I can tell you something that one of the reasons why the Telstar is supposed to be good is that the total length of the edges is rather small. If you take a standard Telstar, would you guess what is the total length of the edges? 4 meters. And my ball, I believe that the total length is maybe twice as long or 3 times as long, and this might have consequences on the drag crisis. It might, I don't know. Maybe you should go to the Eiffel Tower and try to drop it.
Any final questions?
I just wonder how you come up with this shape. You play or try and error, or you just use your theory?
You know, it's Telstar. Instead of this, I took this.
Oh, you do have some.
Y is sine x.
Okay.
Sinusoid.
Okay, thanks. That's why I'm curious.
Not much creativity.
Yeah, thanks.
Thank you very much for your talk. So just to be sure that I retained very well, so you said that if the ball is smooth, so if it's a sphere,
ball, yeah.
it's not such a good thing for because of the turbulence. So
Yeah.
it's true. So
This is the observation of Eiffel. He observed that this is interesting. In his paper, he published a paper on this drag crisis and made comparisons between a perfectly smooth ball and a ball which is rough. And his consequence is that perfectly smooth has the lowest drag crisis.
So for a soccer ball, it's not the purpose to do it as perfect sphere. Or
No, exactly. Yeah. This is why the Telstar is good. It's not a perfect sphere. And again, to answer the question that you asked about the sphericity, so to speak, of the Telstar, I told you that the experts have computed that if you want to have a Telstar which is as round as possible, it's better to have hexagons which are not quite regular. And indeed, I did myself. I measured on the ball the length of the hexagons, of the size of the hexagons, and there's a slight difference between the 3 of them are shorter than the 3 others by about 5 millimeters to make it rounder.
So I think this is a good time to conclude. This is the end of the Q&A session and the presentation, so if you could join me in thanking Professor Ghys again for his very interesting presentation.